Okay, looks like we're set now. You'll have to pardon me because I haven't really got a chance to look at things since last week. So I'm not sure I remember everything we were doing. But we're looking at linear first order DEs. The general form is a1x, some function of x times dy dx, plus a function of x times y, plus equals a function of x. So there are only two terms involving y. One is the function itself, y, and the other is its derivative. And they are linear in the sense that neither one is, well, they're both to the first power, and their only coefficients are functions of x. Okay, so what I thought I would do is a few more examples. Let me see. Make sure I got 352. Just 4. Okay. And I'm going to start with let's talk a little bit about, oh yeah, I don't remember what I had in mind here, but remember that we solved this. By using an integrating factor. And this is not the only type of function we're going to, or DE we're going to use integrating factors on, but we take the integral of, write it in the standard form first. Okay. We have the general form. We write that in standard form, basically divide through by a1, the coefficient of dy dx, so that it's 1. Take the integral of the, once we've done that, put it in standard form, take the integral of the function in front of y. Take e to that power, and that's going to be our integrating factor we call mu. Because once we've done that, then the left, and then multiply through. So we have mu of x times dy dx plus this function of x times p of x y equals mu of x q of x. Okay? And while this looks awful, what we've done on the left side is make a perfect derivative no, not mu of x, p of x. We made a perfect derivative of mu of x times y. So that means we can then take the integral, and whatever our integrating factor was, mu of x times y, will be the integral of this mess over here on the right. And sometimes it is a mess, but it at least gives us a plan of attack on these. Now, what's on the right-hand side isn't necessarily guaranteed to be integrable, but so we need to look at some ways of approximating it. And here's one that's built into your calculator. It's a definite integral approximation. To integrate a definite integral from a to b of f of x dx, on the calculator, it does a real good job. It's the function int, which you look under the math. Let me see if I can pull up the calculator. Some days I can, some days I can't. If you look under math, then somewhere down here is the function integral. And to use this, you would enter the function first, then the variable that you're integrating, then the lower and the upper limits. So for instance, we're going to do this on this e to the negative x squared dx. This is, you can't find a closed form for that guy. Okay. There is no antiderivative we can come up with, so we're going to do it on the calculator. So go to math, and then down on the 83, it's down to number 9 is the function integral. Okay, the function is e to the negative x squared. The variable of integration is x. The lower limit is 1, and the upper limit is 3. And we get 0.13938. So this is approximately. Okay. And that's good enough for what we're going to do in this class. If you need to use some sort of approximation thing, then the calculator function integral is good enough. You can also use it to graph integral functions, but I think this is the only way we're going to use it here. I want to do an example of that, and that's using its number 3, page 52. This is an example in the book, okay? Not one of the exercises, but one of the examples. Okay. So let's get full screen here. Okay, example 3, page 52. And this too is one of these messy ones, as they all are. Yeah. We have this differential equation, prime or dy dx if you rather, plus y equals the square root of 1 plus the cosine. We have initial value of y of 1 equals 4. Okay. We're not asked to find an explicit function. We're asked to find what the value of this function is at 2. Okay. So I'm not going to end up with some y equals some great big long thing with x in it and then plug a 2 in necessarily. Okay. So let me rewrite it here in terms of our standard form. Okay. It's dy dx plus 1 times y. So in other words, p of x is a linear dE. So it's p of x equals 1. And q of x is the square root function. 1 plus the cosine squared. Okay. So I'm going to go off to the side and do my integrating factor thing. We take the integral of p of x dx, and that just gives me x. And the integrating factor is e raised to this power. Okay. So it's e raised to integral power. So in this case, it's a pretty simple one. Now we multiply through this equation, well, either one of this equation, by e to the x. I'll extend the page a little bit so we can see it. So e to the x times dy dx is e to the x times y equals e to the x times 1 plus the cosine squared. Okay. Now, the left-hand side is a perfect derivative. It is the derivative of a function e to the x times y. So when we take the antiderivative, we just get e to the x y equals, and then we've got this horrible mess here. E to the x times the square root of 1 plus cosine x dx. Well, I don't care what kind of integral table you get. It can be the one I gave you is from the calculus book, or you can get great big books of integrals. I don't think you're going to find this one in there. So we're not going to be able to evaluate that thing. Okay. Let me write down what the explicit answer is, but as I said, we're not going to be able to find it. Y equals, we divide by e to the x, or multiply e to the minus x. E to the minus x times the integral of e to the x square root of 1 plus cosine squared x dx plus some constant. Okay. I don't want, that's as explicit as we can get. And that's not what we're after, though. We're after just to find the value of the function at 2, not an explicit formula for the function, but just what the value of the function is at 2. So we're going to back up a little bit to, instead of looking at this final answer here, we're going to back up one step here. Okay. And do a little bit of, well, I don't know, a little bit of cleverness here. I know what the value of the function y is at 1. I'm trying to figure out what the value is at 2. So I tell you what, let me just insert a new page here and start. Okay. So we've got e to the x y equals integral e to the x one find it's supposed to be 1. Find the value of the function at 2. If when x is equal to 1, I know it's equal to the value of the function is 4. Okay, well, we're actually going to do a little bit of cleverness here. To make it okay. Since the integral is e to the xy, then the integral from 1 to 2 will be e to the xy evaluated from 1 to 2, which is e squared times y of 2, which I don't know, minus e to the first power times y of 1. That number I do know, equals this thing, integral from 1 to 2 of e to the x Okay, well, we can do this on the calculator. At least we can approximate it on the calculator. So on the calculator, this is, tell you what, maybe I ought to go run through this again. Nope, I believe it is. So go through the integral approximation thing on the calculator. It's 4.841446, and when I first did it, I got 6.604, and then I realized I had my calculator set in degree mode. I teach trigonometry, and we're doing degrees there, and then I come in this class and forget. Then I go back in the other class and forget I've changed back to radians. Okay, so I've evaluated that integral, at least. And let's plug in what we do know. This is an e squared. Y of 2, I don't know. Y of 1 is 4. So what we can do, if we want to figure out y of 2, I can solve by adding 4e And then if I divide through by e squared, I get that y of 2 is approximately 4.84, copied it down wrong, 1446 plus 4e divided by e squared, which looks funny, but it's certainly something you can plug into a calculator. That's about 2.1267. So we never were able to get an explicit formula for the function, but that because we knew an initial value, we were able to use the program to approximate the value of the function there by approximating this integral on the right-hand side. I have in mind something like this to assign. Okay. Now I'm going to do another linear function that's going to take probably 2 or 3 boards to do, but it's a very very important function, important type of DE. And that's problem number 31 at the end of this section. So 31 on page 55. So we have a simple looking DE, linear DE. dy dx, it's already in standard form, plus p of x, y equals x. Now there's no explicit formula given down there for p of x because it is a piecewise defined function. It is 1 if 0 is less than x is less than or equal to 2, and it's 3 if x is bigger than 2. So in other words, this function there, this coefficient function, changes drastically. And this happens a lot. We could be talking about a circuit and somebody flips a switch all of a sudden. So the solution is going to change. There was one problem I was going to work out, but it just took me about a half an hour to do and was really, really messy, where it's one of those mixture problems where you're going along just fine, like the example I did the other day, but at some point a hole is poked in the bottom of the tank. So there's a discontinuity here. Something immediately changes. Okay, so something is turned on at x equals 2. So what's the solution to the equation then? What we do is we find oh yeah, and there's an initial value too, I left that out. The initial value is y of 0 equals 1. Okay, the plan of attack on this is let's just work with the top function in p of x. Let's solve dy dx plus 1 y equals x with the initial condition y 0 equals 1. Get a solution for that. Okay. And that'll work from 0 to 2. Now, then once we get to 2, we'll get a solution here for p of x equals 3, and we'll have to work with the constant so that this new solution matches up with the one we had that worked from 0 to 2. So that's the idea. Okay. So in other words, something a switch was flipped. A hole was poked in the bottom of the bucket or something. So first thing is let's find y of x, okay, or just the top equation. We'll solve this like there wasn't a second part. All right. So it's dy dx dy dx plus 1y equals x. So our integrating function is e to the integral of 1 dx is e to the x like we had on the previous problem. Multiply this through okay. Then we have e to the x dy dx plus e to the x times y is e to the x times x. The left side is the perfect derivative. This integrating factor gives us a perfect derivative. This is just the derivative of e to the x times y. So we'll integrate both sides. Integrate the left side, you get e to the x times y equals the integral of e to the x times x dx. And this is an integration by parts problem. If you want to go through it, I'm just going to cut to the solution. You know, u would be x and du would be e to the x, dv would be e to the x dx. Okay. But this is, or you can look it up in the table. This is x e to the x minus e to the x plus some constant. So e to the x y equals all of that. Let me write that down. E to the x y equals x e to the x minus e to the x plus a constant. Multiply through e to the minus x so that I get y explicitly. Okay, so the y is gone by itself. I'm going to take e to the minus x times the first term. E to the x and e to the minus x cancel. E to the minus x times the second term, well, e to the x and e to the minus x cancel, leaving negative 1. And I have c e to the minus x. This is the general solution of this dE when the coefficient function is 1. And what we need to do now, we haven't used, is the initial value. When you put a 0 in for x, I should get a 1 here. So 1 equals 0 minus 1 plus c e to the 0. So I get 1 equals minus 1 plus c. So 2 equals c. So let me summarize this. So, sorry. For x between 0 and 2, the solution is y equals x minus 1 plus 2 e to the minus x. So I've just ignored the second part of the piecewise defined coefficient function. And I got a solution that satisfies the initial value condition and that. Okay, now comes the hard part. The hard part is we have to start from here to to find a solution for this dE that satisfies the second one here. So let people catch up. By the way, I'm assigning you a problem where not where the p of x function is piecewise defined, but where this function over here is piecewise defined. It's the same sort of thing. You just start with whatever the top half of the function is, solve that, and then you've got this next part. We have to do a solution. Okay, so we've got this. Now, let's see. Let's do a new page, and I'll put that here. So. Yeah, X. Okay. This goes from 0 to 2. And we're interested now in this part of the p of x. I've already done the first part, so don't even write it down. So we just hold on to this thing. And it's dy dx then plus 3y equals x. Now, we start at x. This is going to take up where x equals 2. So we need not the initial value we had before, which was when x equals 0. We now get our initial value, okay, since whatever our solution to this must match up to the one we already had that works from 0 to 2, our next initial value is gotten by plugging a 2 in here. Okay. 2 minus 1 plus 2e to the minus 2. Okay. So it's 1 plus 2e to the minus 2 is that's going to tell us how to do our constant. By the way, I have to see something first. So, where am I here? P of x equals 3. So we take the integral of this, and our integrating factor is e raised to that power. Both sides by that. So I have e to the 3x times dy dx plus e to the 3x times 3y is e to the 3x times x. The left side is the perfect derivative of my integrating factor and y. So when we integrate both sides to get our solution, we have e to the 3x y is the integral of e to the 3x. Can't read that. X dx, okay. And like before, you can do this by integration by parts. U would be x, so that when you take du, it would just be dx if it gets simpler. And dv would be e to the 3x dx. But I'll go ahead and just write the answer down. This is 1/3 x e to the 3x minus 1/9 e to the 3x plus some constant. I'll use the same letter here, even though I probably ought to use something else, since there's no reason to expect this value of constant to be what we had before. And then if you multiply through by e to the minus 3x, so that I have just y by itself. So it cancels out the e to the 3x, so we have y equals, it cancels out an e to the 3x in the first one, 1/3 x minus 1/9 plus some constant times e to the 3x, negative 3x. Okay, and we'll wait a second there. Now, this constant has to be such that, of course, when you change the constant, then the function is it might move up or down, or it might change a little bit, but it's a different. You'll have a different version of this e to the negative 3x type of function. It might be a little wider or a little skinnier, or it might shift up or left or right. But we have to pick a value of c here so that at x equals 2, this new function matches up with that one. So that means that when x equals 2, I should get this value when I plug it in to the new function. Okay. So let's do that. Okay. Let me see. Is this one? Oh, there it is right there. Okay. Should have stuck with it. So, yeah, there's. I got a graph up here in a minute. So let's extend this. Y of 2 equals 1 plus 2e to the minus 2, and that should be 1/3 of 2 ninth plus c e to the minus, put a 2 in minus 6. Okay. So now we got some messy little algebra to do. Let's see, 1/3 times 2, that's 2/3 minus 1/9. That's 5/9 plus c e to the minus 6. Now, if you multiply through by e to the, I want to do that. Yeah. Let's, not quite ready for that. Let's move the 5/9 over to the left. Subtract 5/9 from both sides. You get 4/9 plus 2e to the minus 2 is c e to the minus 6. We're trying to solve for this constant c. So now if we multiply through by e to the 6th, then I'll just have c on the right. And I'll have 4/9. Everything's got to be multiplied e to the 6th. E to the 6th. 2e to the negative 2 times e to the 6th is 2e to the 4th. Okay. And this is the constant. This is the constant that goes in here. Okay. And again, I'll let people kind of catch up. Then I'll put the final answer all together here. because this constant works for the second half of the answer. So as I said, this constant goes in up here for C. And I know the answer is going to look really strange, but I'll put it all together here. I got it. That's okay. So here's the original statement of the problem, and here's our solution. Piecewise defined solution. X minus 1 plus 2e to the negative x if x is between 0 and 2, 1/3 x minus 1/9 plus, parentheses, 4/9 e to the 6th plus 2e to the 4th times e to the negative 3x if x is bigger than 2. And I'll tell you what I'm going to do. I'll be right back on this page. I'm going to go to the next page and grab the graph. Here's the graph of that thing. So from 0 to 2, the first function looks a little bit, well, sort of parabolic, and then something drastic happens at 2. And from 2 on, we have this second function, and that's what the solution to the DE looks like. And I'm going to assign number 32, which is the discontinuity is not in the coefficient of y, it's in the function on the right side, what we usually call q of x. And you work it the same way. You'll find a solution for the first part, figure out what the constant has to be, find a solution for the second part, and figure out what that constant has to be so that the solutions piece together at that discontinuity point. So even though the original differential equation had a discontinuity in it, the solution doesn't. Okay, so fun stuff here. It's really, it's terribly messy, but I think I like the ideas here. We're going to do just a little bit from the next section, which is on exact equations. So let me see. Do I have anything here? No. First, let's get used to a little different looking notation when we do exact equations. If we had something like this, dy dx equals, let's just say it's f of x, y. Then, do I want to do that one? We could write this dE as in differential notation. In other words, not write it as a derivative, but dy equals f of x, whatever dx. And we're going to be looking at some dEs that are kind of written that way. They're not written as a dy dx or a y prime. but basically the denominator, so to speak, of the dy dx is multiplied through, so something's times dy and something's times dx. So, for instance, suppose we have a differential equation written in the following way as some function of x, y times dx plus another function of xy times dy equals 0. Now this is a first order DE because we don't see a d squared x or dx squared or d squared y or anything like that. And if you want to make it look like an ordinary DE that we've had so far, you can divide through by dx and it would look like your first order DE. Now this might be linear, this might be separable, okay? We don't know yet. Okay. Now, I'm going to go to pull a calculus 3 result out here. If you haven't had calculus 3, that's okay. Okay. But we're not going to do too much here, but if I know some of you have had it. If we had, say, some function of x and y, the differential of this what you would do to form the differential. Now, ordinarily, if you have a function of one variable, dy would be in f prime of x dx. But here you have a function of two variables, so the differential, the d of whatever this function is going to be the partial of f. That's supposed to be partial. Partial of f with respect to x times dx plus the partial derivative of f with respect to y times dy. And we'll do a few partials, but the idea on a partial is that if you were doing the partial of f with respect to x, you would take the derivative and treat x as a variable, and anything that wasn't x would be regarded as constant. So if you have a y, if you're taking a partial with respect to x and it's got a y in there, y is just a constant as far as x is concerned. Okay, so that's the differential of f of xy. Now, if you take the integral of what's here on the left, you'll get f of xy back. So here's what we've got here. That's a calculus 3 result. So suppose we have an expression like I had up here, a function of xy times dx plus a function of xy times dy equal to 0. And that we have some big function f of x y with the partial of f with respect to x to equal the m function, the partial of f with respect to y equal the n function. Okay. Then this equation I've been putting this star by it's an exact differential like I have here in the calculus 3 result. Okay. All right, just a little bit more here. Then this equation, and I've got two things with a star on it, but they're both the same thing. Okay. Then this differential equation we started with here can be thought of as this, which means it's an exact differential. Okay. Then the dE star is called an exact equation. And the solution is well, you've got to have whatever this big function f was, equal a constant. Might get a chance to do one. These are kind of interesting problems. What in calculus 3, you take partial derivatives with respect to one variable or another. What we're going to do here is kind of take partial integrals. This particular coefficient will be a function of, a derivative with respect to y, so we'll want to integrate it with respect to y to try to figure out the function it came from. This is a partial with respect to x, so if you want to get back to the original function, we'll try to integrate it with respect to x. And these are supposed to come from the same function f of xy, so we have to somehow put those two together. And let me see if I've got a simple one, and this is all we're going to do. This is number 3, page 64. Yeah, I think this one. Okay. We have, no, I don't want to do number 3. Okay, let's do 6. We'll come back to do number 3. Let's do number 4, page 64. Y e to the xy plus 2x dx plus x e to the xy minus 2y dy. Now they ask if this is linear and if this is separable, and it's neither one. But we want to see if we can find some function f of xy. So a formula with both x's and y's, so that the partial of f with respect to x is what's in front of dx, y e to the xy 2x, and partial of f with respect to y is what's in front of the dy. So this is kind of a little game we play here. So let's see. Okay. This y e to the xy plus 2x, well, if that's the partial with respect to x, then it meant we had some formula with x's and y's, and we took the derivative with respect to x, we got this. So that means if we integrate this with respect to x, treating anything that's not an x, that's just a constant. Okay. We see what we get. Okay. Some of that's easy because it'd be easy to do the 2x part. The first term y e to the xy looks tough, but y is just a constant. X is the only variable. Okay. So let's do the easy one here. And only constant, you're going to have an e to the xy. Now, what happens when you take the derivative with respect? You're going to have this. I just got to figure out what kind of coefficients we have here. If you take the derivative with respect to x of e to the xy, remember y is a constant. It's going to be e to the xy, okay? And then you take the derivative of xy with respect to x, just y, because y is just a coefficient of x. So actually, that is the integral of those two, plus we pick up a constant. Now, this is not a constant. This is a constant as far as x is concerned. In other words, it doesn't have any x's in it, but it might have y's in it. It might just be a plain old constant, like a 4 or something, or it might be a y squared or something because, or a, you know, e to the y over the natural log of 1 plus the cosine squared of y. Okay, it's just whatever this last term is. As far as x is concerned, it's a constant. It has no x's. Okay, do the same thing here. Okay, this was the derivative with respect to y, so if we're trying to recover the original function, I'll integrate this with respect to y. So we had some function formula of x and y. We took its derivative, treating y as a variable and x as a constant, and we got this. And like the previous one here, if x is just a constant, then an antiderivative of x e to the xy is e to the xy. Integrating with respect to y. And if you don't believe me, take the derivative of this thing with respect to y. It would be e to the xy, and then take the derivative of xy, it would be x. Okay, so. Now take the antiderivative of 2y with respect to y, minus a y squared, and here you pick up a constant, but it's not necessarily a number constant, it's a constant as far as y is concerned. That might have some x in it. This could be an x or something because when we take the derivative with respect to y, we got this. Now, what happens when we put those two functions together? Can you tell me a big formula for f of xy? Well, both of these have an e to the xy in them. In the first term, we've got an x squared and some function of y that's a constant. Well, here's a function of y. In the second one, we have our minus y squared plus some function of x, which is a y constant. Well, there it is right there, the x squared. And the solution is just some, well, I've already used c twice, and I shouldn't have. Let's just call it k. So that's what we do with exact equations, is we see if we can make, if they're exact. Okay, so look at the dx coefficient, integrate that as a function of x. In other words, use the power rule on x, use whatever it takes, and you pick up a constant term. Now the constant term is going to be a constant as far as x is concerned, so it may actually have y's in it. Go to the second function, the coefficient of dy, integrate that with respect to y, and you pick up a constant there, which is going to be a constant as far as y is concerned, so it might have x's in it. Compare those two things together. You've got an x squared term by itself in the first one. You've got a constant of x in the second one, so that's what your constant x is. Your your C of x is. The first integral, you pick up some constant that may have a y in it, but not an x. When we took our second integral, we picked up a minus y squared. It doesn't have an x in it. So that is what the thing is. So put them all together, equal some honest to goodness number constant. Okay. And that's exact equation. And we will do more of those next time. Okay. Now, I am really, really, really far behind in this class. I mean, terribly far behind. Almost as far behind in this class as I am in the modern algebra class. But have I given you problems on 54 yet? I don't. I told you, but did I give you the rest of them on 54? Okay. Didn't think so. So, page 54. Numbers 3 and 4. Now those are just identify. Okay. 7 and 13, those are find the general solution. Okay, and so it's going to have a constant in it. 17 is find an initial value problem, so that's going to have a, you're going to figure out what the constant is. 25 is like what I did at the start. Oops, back up here, let's do 23. Didn't notice. Radioactive decay problem. I did some exponential stuff earlier, so that shouldn't be too bad, but there's an example you can look at as well. 25 is like what I did at the start. You're not going to get an explicit solution, but you can figure out what an approximation. Okay. 28. '28 reads like a tough problem, but unless I worked it wrong, it's not very hard at all. You just need to understand what they're asking. It doesn't really involve any work. You're supposed to show that something is a solution, so that means take the derivative and show that it satisfies that. Okay. So you're not really finding solutions here. They give you the solutions. You're supposed to verify. And then 32 is the tough one. It's when this outside function, the q of x on the right-hand side, fails to be continuous. Okay, and you solve it a lot like number 31. So expect it to be long and messy. Okay, I will have stuff back. I had to win Thursday, I promise. If I don't grade it, then I'll just give everybody perfect on all of them. Okay. I promise that. Okay, and that's all I can think of.